Hi, my name's Trent Carter, and we're here with Michael McKinley, the designer of the Adjustable Tuttle Box. Michael, can you give us a brief introduction, history story of the original Tuttle Box and how we got to this point today?
Oh, absolutely, Trent. It's so fun to be here talking about the history of these products and where we're going in the future. So the original Tuttle Box was developed by Larry Tuttle in 1983 as a necessity to be able to take the loads of the high performance fins that Larry Tuttle was developing at the time. The story that he tells is literally he would give fins to the world-class riders at the time, launch from the beach, and within 20 yards, they'd rip the entire box out of the board. And so it was clear that we need to have a fundamental design change in order to take the stresses that we were seeing with these new high-performance fins. So Larry came up with this really beautiful design, simple tapered elements on the head of the mast, simple parallel faces, and simple barrel nuts to take the compression loads into the board. And so from 1983 on, literally over 40 years, the design has remained ostensibly unchanged from his original specifications. And it's so cool to see how some really elegant engineering done once solves a problem for several decades.
That is awesome.
So we can take that basic design, and it was strong enough to carry the loads of the early hydrofoil systems that we see. The first foils on the market all have Tuttle boxes.
Okay, on that note, so the first days of foiling, all the boards had these Tuttle Box systems. It since has gone away from that to the double US track system. Now it seems like we're coming full circle back to these Tuttle systems. Can you give us any reason why, what's the case? What are the advantages of the Tuttle system, especially for foiling, over having a plate mast and with the US boxes?
Yeah, absolutely. We can walk through that. So as you mentioned, many of the early foils started with a simple Tuttle construction. And there's a big advantage there. It's exceptionally stiff. It's a very efficient use of material. You can imagine if you think about how the carbon fiber is laid, we have straight unidirectional fibers all the way through the head of the Tuttle Box. And it's very easy for us to take that load into the board. At the highest stressed areas, we have very efficient load transfer with the Tuttle. So this system is light, it's stiff, it's relatively easy to use and maintain. And as long as you're staying within one brand or brands are compatible, it doesn't matter that you can't move the position of the foil.
Right.
The problem is, as more and more foil companies came to market, the optimal location for the mast ends up being up to 3 inches different between brands. And so suddenly there's a need to be able to adjust the location of the foil, or if you're a board manufacturer, you want to have a board that's compatible with a lot of brands. The only option was an adjustable track system to allow you to change the location. From my experience, I was only riding Mike's Lab. I was optimizing the perfect boards for Mike's Lab. And so I have a specific formula for the location of the Tuttle, plus or minus 1/8 of an inch. Like, it's perfect. It never needs to change. And if you need to make a slight change, you move your foot strap just a little bit between riders. The problem is if you need to go between brands, or if you need to go between disciplines, let's say you have the same board for wing foiling, parawinging, downwind, the location of the foil might need to change, or the angle of attack of the entire hydrofoil system relative to the board might need to change.
Of course.
And so suddenly it became clear that I needed something better. I wasn't willing to compromise with the tracks. I wanted to stay with the optimal performance of a Tuttle mast and still allow some adjustability.
All right, so what challenges did you run into trying to design and make this adjustable Tuttle Box system? Was it harder than you expected? Did you run into anything bizarre or crazy, or is it all pretty straightforward, cut and dry?
It's a great question, Trent. So it's very challenging to go from a known quantity that the entire industry knows and understands in terms of the performance to a totally new system. And so my first goal was to make something that Ken loved. You know, I was making this product for myself and for my friends. And I knew if Ken thought it was stiff enough, then we were hitting something that was really going to be cool.
Yeah.
So I completely went from blank sheet of paper, redesigned the laminate schedule for this box so that it maintains the stiffness of the original box, as well as allows the adjustability and is very lightweight. So we want to have a system that is compatible with every Tuttle foil on the market. And that's complicated because the hole location, the angle of the screws is different between brands.
Okay.
And we want to have something that we can adjust to hit different disciplines and potentially different foil brands. Again, all while maintaining something that's very light, extremely stiff, exceptional high performance. We want no compromise with this box. So I went back to the drawing board, designed something from scratch that I'm super excited about. And I love it when people ride it and they say this thing is as stiff as they've ever experienced a connection to the board.
Yeah, I can attest. It's insanely stiff.
I appreciate it. That means a lot. I spent a lot of nights trying to make this thing stiffer, a lot of prototypes. I came up with some innovative ways of testing these boxes in the board and outside the board so that I could compare where we were. So we had a known stiffness quantity with the existing design, and I have a new stiffness element. So my goal was in the middle of the box, when this thing is mid-span, it needs to be as stiff or stiffer than the existing system.
Okay.
And from first principles, when you have a longer beam, a longer span, the stiffness goes down.
Of course.
So something has to give. How do we do that? And we get that with the change in lamination schedule.
Okay.
And with some shim design.
Okay, interesting.
Yeah.
And can you explain us the shim system? So this box is longer than the actual Tuttle itself. So how does the shim play into that?
Yeah, thanks. Great question. So the shims are designed to be exceptionally simple and user-friendly. Right now we're seeing basically these are 1-inch shims. They're designed to seat in the box, and it's kind of a set it and forget it system. So those are in there, they're not coming out. If you want to take them out, you can push them out from the top, or you can kind of pull them out. The production version for the Slingshot Project Drag board will have a screw to retain them in the board.
Okay.
So my goal is to give a user a board that works perfectly right out of the bag. I mean, I want to unwrap it and go ride waves and crush. So we can have those shims come from the factory just perfectly dialed. But then after you test it for a while, all of my friends say, oh, I want to tweak this. I'm going to try a new foil. I want to try something different. Then we can start to pull those shims out and change either the position. So we change that by moving shim from one side to the other. Okay. Or we can change the angle of attack. So we have different shims for that as well.
And then you could also, by changing both shims out, right, you can either move it further forward, further back too.
Correct. Right? So kind of demonstrating that. So here's the foil all the way back. And we'd have the two 1-inch shims in the front. Or we can move the foil to a position where there's one 1-inch fore and aft, or two all the way in the back.
Awesome.
Yeah. So that's the basic adjustability. And then there's a more advanced adjustability, which allows us to do angle of attack adjustments. So when we're riding Mike's Lab, I design my boards to be perfect. We're talking 3.5 degrees between the deck and the foil. And that's something that people weren't even really talking about. You know, you buy your gear, you put it together, you don't really think about how that angle of attack changes. Right. This is something racers were thinking about, people where it really matters. But when you're riding a wave garden here in Maui, you know, some boards feel great, some boards don't, you don't know why. Oftentimes that could be the fact. Okay. So we can tune this now between brands because some brands prefer to be a slightly different angle of attack, and we tune it between disciplines. Some disciplines, when you're going slower, say downwind, say prayer wing on big waves, when you're stashing a lot and trying to ride swell, typically your angle of attack needs to be a little bit.
You're in a lower lift environment.
You got it. That's precisely right. When you're going fast, when you're trying to boost, often you need higher angle of attack. It feels better to have a little more front push pressure, so you're not feeling pulled over the board. You have that ramp that you're pushing into. Okay. That's the basic idea. Awesome. I really like it. I like that you can go forward, back, and then also shim it up and down with the angle of attack. It all makes sense, and it's easier than... It makes sense and it's easy. It's a beautiful design. Thank you. I think the goal really is, you know, my board company, when I make my boards, I give it to them in a perfect this is Mike's Lab optimal position.
Mhm.
And then I set the shims for Mike's Lab optimal.
Mhm.
And then I'll get a call a few weeks later and say, you know, I got this new Slingshot stuff. Where should I put it? Well, let me give you the Slingshot optimal shims.
Wow.
And so suddenly we have this board that is, again, perfect. Because that's one of the downsides of the tracks. Is you get too much adjustability.
Yeah.
There's a guessing game. Where's optimal?
Yeah.
You know, even within brands, it's not always clear where the perfect position should be for that setup.
Wow, how interesting. So you can just take a look, you can look at the angle of attack of the foil, look at the mast, the rake and the mast, and then decide, okay, I'm going to shim it forward or aft, and then change the angle of attack a little, and this is going to be perfect.
Yeah, we can do it from the board design in CAD.
Okay, wow.
So we can look at the center buoyancy of the board, we can look at the center lift of the foil, and we say this is the optimal location. And it's independent of rider size, which is the coolest part. So it's a little bit sensitive to rider, but you can adjust that with your feet. Whereas, you know, you could take here in Ka'a Beach, most people have it dialed. They're really good. They have to. It's a necessity because the conditions are really formidable. It's experts only some days. But when you're trying to begin, you have no idea where the best position should be. You know, it's not clear where that should be.
And this makes it clear.
This makes it clear.
Awesome.
And this is a system that's good for an intermediate to an advanced rider.
Okay. So you kind of just talked through all the performance advantages of particularly this Tuttle system, but in general for Tuttle systems, what separates it? What brings it a level above a plate mast in terms of performance?
Yeah, that's a great question. So right off the bat, you can see this box. This is designed to be 6 inches thick. This is how I supply them. The top of the box is cut to be the top of your board. So you have this unbelievably strong carbon connection, an I-beam, from the bottom of the board to the top of the board. So suddenly the board is acting as this unbelievably stiff unit. And I think that's something that you experienced.
Yeah.
It pumps better than anything. It carves super hard. It doesn't feel like you're losing energy into pumping a marshmallow. And a large percentage of that is having the correct transition of forces from a super stiff mast into a super stiff board.
Right. You could have a super stiff mast, and if your box system, whatever, is super soft, you're losing anything.
That's correct. And I've been able to quantify that by looking at, I can take a mast and clamp it rigidly, measure the stiffness, take the mast in the board, clamp it rigidly, and measure the stiffness, and suddenly you see, the connection here is I've spent $2,000 on the fanciest, highest end, high modulus mast, but this ends up being the limiting factor.
Wow.
So I went back to the design and said, all right, how do we get this to be a perfect match? We want to match the stiffness all the way through. And suddenly you can start to feel the smallest little bumps in the water. The whole system starts to sing. And that's because you're not losing energy in the transition to the board itself.
It's like a perfect kinetic chain.
Perfect kinetic chain, you got it right. So that's a big advantage here. And there's 2 reasons. So one, we have this solid carbon connection from bottom to top. That's standard with the Tuttle Box. 2, now the Tuttle Box is slightly longer. So we have a larger moment that we're able to transfer through the board. And 3, because we're preloading the screws from the deck into the mast, you're able to generate enormous preload as you tighten those screws. Whereas with a plate mast, the preload is only happening at the bottom interface.
Yeah.
You're not able to preload from the top to the bottom of the board.
You're using that whole strength of the entire board.
Absolutely. And so the last piece is, because of the taper on the Tuttle head, you're generating hundreds to thousands of pounds of preload force through the bolts. And then you have a multiplier because I have a wedge of the actual Tuttle itself. So it's optimally loading the strands of carbon in the box itself to get you an exceptionally stiff connection.
That's incredible. Well, Michael, thank you very much. I really appreciate you talking through this. Beautiful design. All works swimmingly. Thank you very much.
Oh, thanks. Appreciate it.